Hello everyone, this is Amit Brahmbhatt here, instructor for CS 110 at Laurel Ridge Community College. Today we are going to go over Chapter 13, Artificial Intelligence, and I'm going to experiment something that you'll find out in just in a moment. So I'm hoping that AI can teach you about AI. Let me go ahead and share the screen. And let's begin.
CSC 110, Chapter 13, Artificial Intelligence taught by Amit Brahmbhatt at Laurel Ridge Community College. Slide 1, Artificial Intelligence. Welcome to Chapter 13, Artificial Intelligence. In this chapter, we explore how machines attempt to model aspects of human thinking, learning, and understanding. We'll look at classic AI concepts such as the Turing Test, knowledge representation, semantic networks, search trees, expert systems, and neural networks. We'll also explore natural language processing and robotics. By the end, you should understand how computers perform tasks that seem intelligent, what limitations they still face, and how AI relates to human cognitive processes. Slide 2, Chapter Goals, 1 of 2. In this chapter, we will examine the types of tasks humans excel at versus the tasks computers handle better. This naturally leads us to discuss the Turing test, Alan Turing's proposal for assessing machine intelligence. We will also introduce the concept of knowledge representation, including how information can be stored and connected using semantic networks. Finally, we'll learn how to create search trees for analyzing decision paths, particularly in game-like scenarios. These goals provide the foundation for understanding how AI systems mimic aspects of human reasoning. Slide 3, Chapter Goals, 2 of 2. In the second set of goals, we focus on expert systems programs designed to capture expert-level decision-making using rules. We'll also explore biological vs. artificial neural networks and how machines learn from examples. Then we'll look at natural language processing, an important field that deals with speech recognition, speech synthesis, and language comprehension. Finally, we'll examine the different types of ambiguities in human language, one of the biggest challenges for AI. These goals prepare us to understand intelligence both biologically and computationally. Slide 4, Thinking Machines, 1 of 4. This slide asks, can you find the cat in the picture? Humans are excellent at recognizing objects even when they are partially hidden, oddly shaped, or surrounded by clutter. But computers often struggle because they need explicit instructions or massive amounts of training data. This example highlights the difference between intuitive human perception and the algorithmic approach used by machines. Visual tasks that feel easy to us actually involve complex processing, which AI is still learning to replicate. Slide 5, Thinking Machines, 2 of 4. This slide asks whether you can perform tasks like counting letters in a book, adding thousands of numbers, or matching fingerprints. Humans can do these tasks, but computers can do them faster, more accurately, and without fatigue. This contrast illustrates a key idea: humans excel at flexible, intuitive interpretation, whereas computers excel at fast, repetitive, rule-based processing. Understanding this distinction is critical to understanding how AI systems are designed. Slide 6, Thinking Machines, 3 of 4. This slide summarizes the contrast. Humans perform well at perception tasks such as recognizing objects or understanding context. Computers perform well at computational tasks requiring precision and speed. AI aims to close this gap by enabling computers to handle tasks humans typically do better. This highlights why AI is challenging. Humans excel in areas where rules are unclear, while computers excel where rules are explicit. Slide 7, Thinking Machines, 4 of 4. This slide defines artificial intelligence as the study of systems that try to reproduce aspects of human mental ability. Examples include recognizing objects in photos, planning moves in a game, or understanding spoken language. AI involves designing algorithms that simulate reasoning, perception, learning, and problem solving. As we progress through the chapter, we'll see how different AI techniques approach these goals. Slide 8, the Turing Test, 1 of 4. Alan Turing asked, "Can machines think?" Instead of defining thinking directly, he proposed a test where a human tries to determine which conversational partner is a computer. If the human can't reliably tell, the computer is said to exhibit intelligent behavior. This was a groundbreaking idea because it shifted the question from philosophy to observable behavior. The Turing test remains a foundational concept in AI. Slide 9, the Turing Test, 2 of 4. This slide shows the setup. An interrogator communicates with a human and a machine through text. The interrogator's job is to figure out which is which. The goal of the machine is to appear convincingly human. This test focuses on language use because conversation demonstrates understanding, reasoning, humor, and context, all challenging for computers. Slide 10, the Turing Test, 3 of 4. Here we see two key concepts, weak equivalence and strong equivalence. Weak equivalence means the machine produces the same outputs as a human but uses different internal processes. Strong equivalence means the machine and human use similar internal reasoning. AI systems today typically aim for weak equivalence, matching results without mimicking human biological processes. Slide 11, the Turing Test, 4 of 4. This slide mentions the Loebner Prize, an annual competition modeled after the Turing test, where chatbots attempt to appear human. Chatbots are programs designed to carry on conversation, often using scripted responses or machine learning. While chatbots have improved dramatically, they still struggle with deeper comprehension and long-term consistency, highlighting the limits of current AI. Slide 12, knowledge representation. This slide asks, how can we represent knowledge? Humans use language, but natural language is too ambiguous for computers. AI requires structured formats for storing and relating information. Two important techniques introduced here are semantic networks, graphs showing relationships between concepts, and search trees, used for decision making. Proper knowledge representation is essential for AI to reason effectively. Slide 13, semantic networks, 1 of 4. A semantic network is a diagram showing objects and the relationships between them. It uses a directed graph where nodes represent concepts and arrows represent relationships. For example, dog rightward arrow is a rightward arrow animal. This structure helps computers reason by following connections. The slide reminds us of directed graphs, which we studied earlier, because the same structure is used in semantic networks. Slide 14, semantic networks, 2 of 4. This slide shows an example semantic network. It might include relationships such as, bird rightward arrow has rightward arrow wings. Semantic networks help AI answer questions by tracing links. For example, if a robin is a bird and birds have wings, then a robin has wings. This ability to infer new information from relationships is a core feature of intelligent systems. Slide 15, semantic networks, 3 of 4. This slide asks what questions you can and cannot ask using the semantic network. You can ask questions that follow the explicit relationships, for example, does a bird have wings? But you cannot ask questions that require information not encoded in the network, for example, details about behavior or color, if those relationships weren't included. Semantic networks work only as well as the relationships they contain. Slide 16, semantic networks, 4 of 4. This slide explains that the network should reflect real-world objects and meaningful relationships. The kinds of questions we want the AI to answer determine what connections we include. If a relationship isn't modeled, the system won't be able to reason about it. This highlights the importance of careful design in knowledge representation. Slide 17, Search Trees, 1 of 5. A search tree represents different possible decisions and outcomes often used in games. Each path down the tree represents a sequence of moves. For example, in tic-tac-toe, each node represents a board state. Search trees allow AI to explore possible strategies. But as the game becomes more complex, the tree grows exponentially, making it hard to search fully. Slide 18, Search Trees, 2 of 5. This slide shows a search tree for a simplified game of NIM. Players choose moves, and each branch represents a different choice. The tree helps determine optimal strategies by evaluating possible future positions. Even for simple games, trees quickly get large, showing why smart pruning techniques are needed. Slide 19, Search Trees, 3 of 5. This slide explains that games like chess are far too complex to analyze completely. The full chess search tree has more possible positions than atoms in the observable universe. Because of this size, even modern supercomputers can analyze only part of the tree. AI must use heuristics and pruning techniques to limit the search. Slide 20, Search Trees, 4 of 5. This slide introduces depth-first and breadth-first search. Depth-first explores one path fully before backing up. Breadth-first explores all nodes at one level before moving deeper. Breadth-first generally finds optimal strategies more efficiently in game analysis because it explores many alternatives early. These techniques help prune large search spaces. Slide 21, Search Trees, 5 of 5. This slide provides a visual comparison of depth-first and breadth-first strategies. AI systems choose between these based on the problem. Breadth-first is more systematic but uses more memory. Depth-first uses less memory but may miss optimal solutions. These approaches form the foundation of many modern AI search techniques. Slide 22, Expert Systems, 1 of 6. Expert systems were one of the earliest successful AI applications. They store knowledge from human experts and apply it through a rule-based system. If-then rules represent the expert's decision logic. An inference engine evaluates these rules to reach conclusions similar to how a human expert reasons. Expert systems are still used in areas like medical diagnosis and equipment troubleshooting. Slide 23, Expert Systems, 2 of 6. This slide lists abbreviations representing outcomes of an expert system for lawn care, such as applying fertilizer or weed treatment. Each abbreviation corresponds to a specific recommendation. These simplified outputs allow the system to categorize decisions based on user inputs. This demonstrates how expert systems translate complex logic into clear instructions. Slide 24, Expert Systems, 3 of 6. This slide defines the Boolean variables that describe the lawn's condition, such as whether it has bare spots, weeds, or bugs. These true/false conditions help the system choose which rules apply. Expert systems depend heavily on correct inputs. If the user misidentifies the lawn condition, the system will reach the wrong conclusion. Slide 25, Expert Systems, 4 of 6. This slide introduces additional data such as the date of last treatment and current season. Combining these variables with rule-based logic allows the system to make seasonal recommendations. The timing information prevents unnecessary treatments. This illustrates how expert systems combine facts with encoded expert knowledge. Slide 26, Expert Systems, 5 of 6. This slide shows the actual rules that drive the expert system. For example, if the lawn was treated recently, apply no treatment. If bugs are present and grass is not sparse, apply bug treatment. These rules mimic how a human lawn specialist would reason. The system applies rules in order until one matches the conditions. Slide 27, Expert Systems, 6 of 6. This slide walks through an example interaction with the inference engine. based on user responses. The system determines the lawn requires a weed-killing and fertilizer combination. This step-by-step reasoning demonstrates how expert systems guide users through a logical diagnostic process. Slide 28, Artificial Neural Networks, 1 of 4. This slide introduces artificial neural networks, which mimic the biological structure of neurons. Before understanding artificial networks, we review how human neurons work. Neural networks allow computers to learn from examples rather than rely on explicit rules. They're used in image recognition, speech recognition, and many modern AI systems. Slide 29, Neural Network, 1 of 5. This slide shows a biological neuron. It receives electrical or chemical signals, processes them, and sends outputs. Understanding this structure helps explain how artificial neural networks take inputs, apply weights, and produce outputs. Biological inspiration forms the basis for how machine learning models operate. Slide 30, Neural Network, 2 of 5. This slide explains the excited and inhibited states of neurons. A neuron fires strongly when excited and weakly when inhibited. This binary-like behavior is mirrored in artificial neurons, which output a 0 or 1 depending on whether a threshold is reached. Understanding these states helps explain how networks classify information. Slide 31, Neural Network, 3 of 5. This slide defines dendrites, axons, pathways, and synapses. These structures help transmit signals through neural pathways. Similarly, artificial networks use weighted connections to combine inputs and produce outputs. This analogy shows how complex behavior emerges from many simple units working together. Slide 32, Neural Network, 4 of 5. This slide shows how synapses weight input signals. A neuron receives many signals, each weighted differently. Artificial neural networks do the same. Each input is multiplied by a weight, and the sum determines whether the neuron activates. These weight adjustments enable learning. Slide 33, Neural Network, 5 of 5. This slide notes that neural pathways change constantly as we learn. Connections strengthen or weaken based on experience. Artificial neural networks mimic this by adjusting weights through training, allowing the system to improve performance over time. Slide 34, Artificial Neural Networks, 2 of 4. Here, artificial neurons are introduced as units that accept inputs, multiply each by a weight, sum them, and output either a 0 or 1. This structure allows networks to detect patterns and make classifications. It's the foundation of modern machine learning. Slide 35, Artificial Neural Networks, 3 of 4. This slide explains effective weight and thresholds. The effective weight is the sum of the weighted inputs. If this sum exceeds the threshold, the neuron outputs 1. Otherwise, it outputs 0. Adjusting weights and thresholds allows the network to learn complex decision boundaries. Slide 36, Artificial Neural Networks, 4 of 4. This slide introduces training, a process where the network adjusts its weights based on examples. For tasks like recognizing a cat in an image, each pixel becomes an input. The network learns which pixels contribute to the cat and which don't. Over time, the model improves its accuracy through repeated adjustments. Slide 37, Natural Language Processing. Natural language processing involves 3 major tasks: voice synthesis, voice recognition, and language comprehension. Voice synthesis allows computers to produce speech. Voice recognition allows them to identify spoken words. Natural language comprehension aims to interpret meaning. Together, these technologies power digital assistants like Siri and Alexa. Slide 38, Voice Synthesis, 1 of 3. This slide explains dynamic voice generation. in which a computer examines letters and translates them into phonemes, the basic sound units of speech. This method allows computers to generate speech for any word, including new ones, but may sound robotic if the phoneme rules are imperfect. Slide 39, Voice Synthesis, 2 of 3. This slide shows phonemes for American English. Understanding how speech is broken into these sound units helps systems assemble words from components. It also highlights the complexity of human speech, with dozens of phonemes and subtle sound variations. Slide 40, Voice Synthesis, 3 of 3. This slide describes recorded speech synthesis, where a computer plays stored recordings of words or phrases. This results in more natural-sounding speech but requires large storage and cannot easily generate new words. Many modern systems combine recorded units with dynamic synthesis. Slide 41, Voice Recognition, 1 of 3. This slide discusses challenges in voice recognition. Every person's voice is unique in pitch, tone, and pronunciation. Factors like accents, mumbling, illness, or background noise make recognition difficult. Because of this variation, recognizing speech reliably remains a major AI challenge. Slide 42, Voice Recognition, 2 of 3. This slide explains additional difficulties. Humans speak continuously, blending words together. Some phrases sound identical, and homonyms create confusion. Humans use context to resolve ambiguity, but computers must rely on statistical models or large data sets to guess the correct interpretation. Slide 43, Voice Recognition, 3 of 3. This slide introduces the concept of a voice print, a visual representation of frequency changes over time. Voice prints help train speech systems by averaging multiple recordings of the same word. They're also used for voice authentication. This shows how speech recognition requires both pattern matching and training. Slide 44, Natural Language Comprehension, 1 of 3. This slide outlines 3 types of ambiguity: lexical, syntactic, and referential. Lexical ambiguity arises when a word has multiple meanings. Syntactic ambiguity arises when a sentence can be parsed in different ways. Referential ambiguity occurs when pronouns are unclear. These ambiguities make language understanding extremely challenging for computers. Slide 45, Natural Language Comprehension, 2 of 3. The sentence, "Time flies like an arrow," demonstrates ambiguity. It could mean time passes quickly, or that you should time flying insects using an arrow. Humans easily discard the silly interpretations, but computers may not. This shows why literal interpretations can fail in AI systems. Slide 46, Natural Language Comprehension, 3 of 3. This slide gives more examples of each type of ambiguity. For instance, a sentence like, "I ate the sandwich sitting on the table," could be interpreted in multiple ways. AI must handle these ambiguities using context, probability, and large language models. Identifying ambiguity is an essential step in comprehension. Slide 47, Robotics. This slide introduces mobile robotics, which involves robots capable of autonomous movement. The Sense Plan Act, SPA, paradigm describes how a robot perceives its environment, decides what to do, and then acts. Sensors provide the data needed to build a model of the world, which the robot uses for navigation and decision-making. Slide 48, Subsumption Architecture, 1 of 2. Subsumption architecture simplifies robotic control by breaking behavior into layers. Instead of modeling the entire environment, the robot performs simple behaviors based on what is relevant at the moment. This reactive approach is faster and more robust, especially in dynamic environments. Slide 49, Subsumption Architecture, 2 of 2. This slide shows Asimov's famous laws of robotics, which govern safe robot behavior. These laws are often discussed in AI ethics but are not used in real robots. They illustrate concerns about safety, autonomy, and human Machine interaction, important topics in AI ethics. Slide 50, ethical issues, IPOs. This slide asks several questions about initial public offerings. The purpose of an IPO is to raise capital by selling shares to the public. The opening price is determined by underwriters based on demand. Individual investors often cannot buy at opening prices because institutional investors get priority. Companies like Facebook and Twitter saw significant price changes shortly after IPO, causing early investors to experience gains or losses. These events raise ethical questions about fairness and market access. Slide 51, Who am I? This slide references a person who won a Nobel Prize and worked in multiple research fields. This refers to Herbert A. Simon, a pioneer in both AI and cognitive psychology. He contributed to economics, decision-making theory, and computer science, highlighting how AI research overlaps many disciplines. Slide 52, Do you know? This slide asks several reflective questions. Television was said to weaken democracy by creating passive audiences, whereas the internet restored participation by enabling discussion and information sharing. The AI language is Lisp, historically used in AI research. Natural language translation turned out far harder than early experts predicted due to ambiguity and context issues. The program acting as a neutral psychotherapist was Eliza, an early chatbot simulating conversation. These questions bring together technology, society, and AI history.
All right, thank you, Microsoft Mark, for presenting the AI class for me. I hope you all enjoyed today's class and looking forward to see you in the next one. Take care now. Bye.